Welcome to this explainer. Okay, so if you've ever found yourself just staring at a massive wall of categorical data, totally wondering how to make any mathematical sense of it all, you are absolutely in the right place. Today, we're going to completely demystify the chi-square test. And don't worry, we're not just going to sit here and memorize formulas. Instead, we're going to use some really clear visual blueprints to map out exactly how this incredibly powerful statistical tool actually works under the hood.
To make sure all this complex stuff is totally digestible, here is our roadmap for today. 1. Decoding the chi-square test. 2. The discrepancy engine. 3. Path 1, the test of independence. 4. Path 2, goodness of fit. And finally, 5. Measuring the effect size. Let's get right into it.
Section 1. Decoding the chi-square test.
Right off the bat, let's establish exactly when you even need to reach for a chi-square test instead of, the other statistical tools you probably already have in your toolkit. The distinction here is crystal clear. Think about continuous data, things you actually measure, like test scores, heights, or time. When you've got continuous data, you're usually firing up a t-test or an ANOVA. But now, flip that. Think about categorical data. This is when your data falls into frequency buckets. We aren't measuring a numeric score anymore, we're just counting. How many people said yes versus no? How many items fall into category A versus category B? When you are dealing strictly with frequencies and counts, that is the true, undisputed domain of the chi-square test.
Section 2. The discrepancy engine.
So now that we know when to use this tool, let's look at the core mathematical formula itself. Honestly, it helps to visualize this thing as a mechanical engine. At its absolute core, that abstract sigma equation operates just like a tangible machine, a real discrepancy engine. It processes your data by doing one fundamental thing. It compares your observed reality, as in what actually happened in your study, against a theoretical expectation, which is what should have happened if absolutely nothing interesting was going on. So data flows in, it gets compared, and a final deviation score pops right out.
The math can look a little intimidating at first glance, but let's break it down into 4 completely logical sequential steps. Step 1, you subtract your expected value from your observed value. Boom, that gives you your raw discrepancy. Step 2, you square that result. Why? Well, because we want to remove any negative numbers so our deviations don't just magically cancel each other out. Step 3, you divide by the expected value to calibrate the weight of that discrepancy relative to its size. And finally, step 4, you just sum up all those normalized deviations. That final sum? That's your chi-square value.
Section 3. Path 1, test of independence.
All right, with our engine built, we've actually reached a fork in the road. Depending on your specific research question, you have to choose a path. Let's cement the difference between our 2 main options here. Path 1, the test of independence, asks a very specific question. Are 2 different variables related to each other? The null hypothesis here assumes they are completely independent, totally unrelated. Path 2, goodness of fit, asks a totally different question. Does my data fit an outside theoretical model? Understanding which of these 2 questions you are actually asking is step 1 of any categorical analysis.
Let's start down path 1 with a real-world example. Picture a study looking at first-year college students versus seniors. We want to know, does knowing a student's year in school actually predict their willingness to participate in a slightly risky experiment? We have 2 categorical variables playing here, year in school and willingness to participate. We are testing to see if one is contingent on the other.
To run our discrepancy engine on this, we need both observed and expected values. But where do the expected values actually come from in a test of independence? This is crucial. They are calculated purely from the data margins. Think about it. If there is genuinely no relationship between being a senior and wanting to volunteer, we can calculate the mathematical expectation just by multiplying the row total by the column total and then dividing by the total number of participants, n. It's driven entirely by the mathematical probability of those margins.
Real quick, before we look at our result, we need to demystify some essential statistical jargon. Degrees of freedom. Sounds intense, right? Actually, it's pretty simple. Think of a 2x2 contingency table like a tiny 4-square Sudoku puzzle. Because our marginal totals are fixed in place, how many cells are actually free to vary? Just 1. Once a single number is selected, say we lock in 32 in the top left, the rest of the cells are mathematically locked in to keep the totals accurate. So for any 2x2 table, our degrees of freedom literally just equals 1.
Okay, pro tip time. Here is an incredibly useful diagnostic trick. Once you've run the math and found a significant relationship, in our case, finding out first-year students volunteer significantly more often, don't just stop there. You can actually examine that final calculation column, the squared discrepancies divided by expected values, to see exactly which specific deviations drove your significant result. The larger the number in that final column, the more that specific cell contributed to rejecting the null hypothesis. It's a great way to peek under the hood of your own data.
Section 4. Path 2. Goodness of fit.
We've mastered testing two variables against each other. But what if we only have one variable and we want to compare it against a theory? That brings us down path 2, the goodness of fit test. To ground this, let's ask a very specific, relatable question. Suppose you survey a group of students and ask them to choose their ideal summer vacation spot across 3 distinct categories: the city, the mountains, or the seashore. Are all these locations equally preferred, or is there a significant bias towards one of them?
Now, here is the absolute defining feature of Path 2. Unlike our test of independence, the expected values here do not come from the margins of our data. We don't use them at all. Instead, expectations come from outside theoretical models. That model might be a famous scientific theory, like a 3-to-1 ratio in Mendelian genetics. It might be historical baseline data from a previous decade, or, as in our vacation example, it might simply be an equal likelihood distribution model.
I need you to pay very close attention here because this is a massive tripping hazard when you're learning statistics. Up to now, rejecting the null has pretty much always been the goal, right? You want to find a difference. But in goodness of fit, a retained null hypothesis is often a wonderful thing. Why? Well, because the null hypothesis says there is no difference between your data and the theory. So if you retain the null, it means your observed data fits your theoretical model perfectly. It's exactly what you predicted.
Let's calculate our expected values for that vacation survey. We had 78 total respondents. Our theoretical model is equal preference, which dictates that those 78 people should be divided equally across our 3 location buckets. Simple math, 78 divided by 3 gives us exactly 26. So our discrepancy engine is going to fire up and compare our observed survey counts against an expected baseline of 26 for the city, 26 for the mountains, and 26 for the seashore.
Section 5. Measuring the effect size. Okay, we've successfully run our engine and answered if a relationship exists or if a model fits. But how big is that relationship? A significant p-value is great, but it doesn't tell you the actual magnitude of your finding. That is exactly why we must measure the effect size. Depending on the size of your table, statisticians generally rely on one of 3 primary tools: the odds ratio, the phi coefficient, or Kramer's V. Let's take a quick look at how each of these gives crucial real-world context to our raw chi-square numbers.
First up, the odds ratio. This one is fantastic because it's incredibly intuitive for everyday conversation. Going back to our earlier student experiment example, calculating an odds ratio reveals a very concrete, punchy takeaway. First-year students were nearly 3 times more likely to volunteer for the risky experiment than the seniors. It translates abstract statistical significance into a highly relatable metric you can easily explain to anyone.
Next is phi, which you'll use specifically for 2x2 tests of independence. You can think of phi as operating very similarly to a standard correlation coefficient. A value hovering near 0 means there's basically no relationship. On the flip side, we use standardized benchmarks to interpret it. A 0.10 represents a small effect, 0.30 as a medium effect, and 0.50 represents a large, highly noticeable effect in your data.
But what happens when things get a bit more messy and your contingency table is larger than 2x2? Say you're comparing 3 different categories of health status against 2 categories of internet usage. That's a 3x3 table. In those more complex cases, phi just doesn't work anymore. Enter Kramer's V. It adapts to the size of your table by using the degrees of freedom from the smallest side, ensuring you always have a standardized, reliable measure of relationship strength no matter how big your table gets. We have covered a ton of ground today, but I want to leave you with this final, kind of provocative thought. The chi-square test is an absolutely incredible diagnostic tool. The discrepancy engine will unequivocally tell you if a difference exists in your categories, and your effect size indices will tell you exactly how big that difference really is. But the math ends there. It literally cannot tell you why first-year students are more reckless, or why people suddenly prefer the seashore. That part, which is honestly the most fascinating part, is entirely up to your human curiosity as a researcher. The math gives you the what, but you have to go find the why. Keep asking great questions, and I'll catch you in the next explainer.